Hello and welcome back. In the last video, we looked at some set identities and we provided some intuition behind why they were true. But in general, intuition can fail us. So we need to have some sort of fail-safe way of showing that an identity is in fact true. And the real problem behind drawing Venn diagrams to illustrate a proof behind an equality of two sets is that it was very specific to the way in which we drew the picture. In our pictures, we had maybe 2 or 3 sets, and we drew them as intersecting in this way. So, according to this picture, there is a location in which A, B, and C all intersect. But that's not the way the picture has to look. If we had drawn it differently, we would basically have to redo our intuitive shading of the Venn diagram for one side of the equation, and then do the shading for the other side of the equation and show that those two shadings are identical. So because there are so many ways that A, B, and C could look, here's another picture. Let's suppose that A is here, B is here, and then maybe B and C intersect, but A has no intersection in common between them. And you can imagine that there's lots of other ways in which we could draw this picture as well. We could have A, B, and C as being what we call disjoint, or we would say mutually disjoint sets. And so when we do these shadings on this picture here, the leftmost one, we're basically saying that there is a portion where all 3 sets overlap. And if we wanted to show without a doubt, case by case, that these two sets on opposite sides of this equal sign are always in fact true, we would have to draw all the possible pictures to show that the sets are equal in all of those cases. That would be a very painstaking process. Now, in general, for 2 sets to be equal, for example, if A is going to equal B, well, what does that have to mean? Well, that means that all the elements inside of A are also inside of B. That is, that for every element that you find inside of A, you have to be able to find that same element inside of B. Similarly, for them to be equal, all the elements that you find inside of B have to be elements of A. And these may seem kind of like they're the same thing, but they're really not. For instance, in this picture that I'm going to draw here, here is B, and here is A. So you can see that anything that I pick inside of A, anything that's inside of A, is definitely inside of B. But there do exist elements that I could pick inside of B. For example, that guy right there is inside of B, but he is not inside of A. So, and by the picture we can see that these 2 sets are not equal. Now the only way for them to be equal is if I draw the picture such that here's A, and if I want to make sure that any element that I pick inside of A is also inside of B, that means B would have to be at least as large as A. That means B would have to be a circle that is of equal or greater size than A. So for instance, if I drew a circle around A, then that would ensure that all elements contained inside of A are contained inside of B. But in order for this second statement to be true, that all of the elements that are in B are also contained inside of A, that would mean that B would have to be the exact same set. So if that is both B and A at the same time, that means any element that I pick inside of here, right there, that's inside of A, well, that element is definitely inside of B. Now if I pick any element inside of the blue circle, like that point right there, well, that element is also inside of A. Why? Because those 2 sets are equal to one another. So whenever we prove set equality, show that 2 things take place. One, that all of the elements in A are also inside of B, and 2, show as well that all the elements in B are also inside of A. So as a brief bit of intuition, if I look at A equals the set 1, 2, 3, and I look at B equals the set 1, 2, 3, 4, and I start off with the question, is A a subset of B? Well, if I look over here and I see 1 is an element inside of A, it's also inside of B. So far so good. If I pick an element inside of A, I can see it's inside of B as well. If I pick another different element inside of A, well, it's also in B. If I pick this third element in A, well, that's also in B. Therefore, yes, this is a valid, or the answer to this question is yes. Now, in order for me to be able to say these two sets are equal, which you can see they're not, is B a subset of A? To disprove this, really, I just have to find one element that's inside of B, namely this guy, which I do not see over here. Therefore, B is not a subset of A, and what does that allow me to conclude? My conclusion is that, therefore, I'm going to use these three circles that look like bowling, like 3 bowling pins from a top view. That means, therefore, A is not equal to B. Okay, so that's by example. Let's take a look at one of the properties and see how we might go about showing that the two sets are equal to one another. So let's start with this one. Prove that A minus B is equal to A intersect B complement. So a little bit of intuition here. A minus B are all the elements that we know to be inside of A that are not inside of B. So when we do this, we start off with an element. So let's start off with part 1. We're going to show that all elements inside of A minus B are also inside of A and B not. So what does that mean? Well, first of all, we're going to say let X be an element that's inside of A minus B. Okay, now we're going to deconstruct that a bit. So let's define, what does it mean for an element to be inside of A minus B? Well, by definition, that means that X is an element of A and X is not an element of B. All right, well, that might seem obvious that we already are seeing that this is an AND statement here, and we have this word AND right here as well. But X is not an element of B. We also want to point out that if X is not inside of B, so here is just a set B. If it's not inside of B, that means it's anywhere but B, right? So for an element to not be inside of a set means it is in the complement of the set. So that leads me to say X is an element of A and X is in B complement. Now you see that really all we're doing here is we're just manipulating words and symbols. And we deconstruct our statement to say that if X is in here, we want to show that it's also inside of here. That means it's a subset, right? If it's in A minus B and we show that it's in A and B complement, that by default means that A minus B is a subset of A and B complement. Well, we're really there already. For an element to be inside of A and B complement means that X is an element of A intersect B complement. And that's exactly what we set out to achieve. We've just established that since X is an element of A minus B, we've shown that X is also an element of A and B complement. Therefore, we've shown that A minus B is a subset of A and B complement. Now, we haven't shown equality yet. We've just shown that A minus B is contained within here. So far, we're only able to say something like this picture here, where we see that the left side is contained within the right side, but we also have to show that the right side is contained within the left side. So to go about doing that, we now have to show that A intersect B complement, that an element that lives inside of there also lives by default inside of A minus B. So we're going to do this exactly the same way. We're going to say let x be an element of the thing, of the set that we know it's in. And now let's show that that element also lives in A minus B, the set difference between A and B. So we're going to deconstruct this statement here. This by definition means that x is in A and x is in B complement. Now, in order to show that it's in A minus B, we need to come up with the conclusion that x is in A and that x is not in B. And then we're actually kind of working backwards in a way. X is in A, and for x to be in B complement, another way of stating that by definition, it means that x is not an element of B. And if x is an element of A and x is not an element of B, that's precisely the definition behind x being an element of A intersect B complement. So since these two are subsets of one another, so I'll just write it like this, since 1 and 2 are true, A minus B is equal to A intersect B complement. So that means what we already know, or what we've already drawn before, if this is A and this is B, then A minus B is basically this portion here. A and B complement just means that you have an element that's inside of A, definitely inside of A, but not in any portion that it shares in common with B. So there's that intuition. This proof method works because it doesn't limit us to exactly this picture. Even with two sets, another way that I could draw this would be for A to be here and B to be over here. So since there's a lot of ways in which the left-hand side, ways in which two sets can be constructed, A could be nested inside of B, B could be nested inside of A, our proof here establishes that these two sets, A minus B and A and B complement, are equal no matter what. Let's go ahead and take a look at one more. So let's say that we want to prove that the complement of A and B is equal to A complement union B complement. This is also known as De Morgan's law, or one of De Morgan's laws. So to do this, we're going to, step one, we're going to show that A intersect B complement is equal to, is a subset of A complement union B complement. And once again, all this boils down to is start with an element that's inside of what you want to show is contained in the other set. So A and B complement. I'm going to start an element in here. I'm going to show that it's also an element of what I'm claiming it to be a subset of. Well, what does this mean for X to be an element of A intersect B complement? Well, A intersect B it means it's an element of A and B. A intersect B complement means it's not an element of A intersect B. So that means X is not an element of A and B. But what does that mean? For X to not be, and I'm just going to draw this picture just for a little bit of intuition, for X to not be an element of A and B means that X is just not in this little football-shaped sliver, but it is anywhere outside of that. So it's anywhere but that football-shaped sliver. Okay, so for X to not be an element of that, that really means that we need to make some sort of leap of faith, right? How do we get from the intersection to the union? So for X to not be an element of the intersection, that means that X is not simultaneously in A and in B. So I'm going to write that down. X is not simultaneously in A and B. All right. Well, that means that either X is not in A or that X is not in B. Because if it's not simultaneously in both, it's clearly not in one or the other. So if it's not simultaneously in A and B, that means X is not in A or X is not in B. This is really the hardest part of this, is to say logically what does it mean. So the picture kind of helps illustrate that a little bit, that it's just not going to be in any place that A and B have in common. So if it's not in a place where A and B are in common, then that means it's either not in one or the other, or perhaps not in both at all. So now we're very, very close. For X to not be an A, remember we want to show that X is an A complement. This means that precisely, if X is not an A, then X is an A complement. Or X is in B complement. And if X is an A complement or X is in B complement, by definition of union, that means X is an element of A complement, union, B complement. And we're done. We've started off with X being an element of the thing on the left, and now we've shown that it's also an element inside of the thing on the right. Now, a lot of times reversing this process is very, very similar, and you can almost always look at your steps in going one way and show that it goes the other way. So now we need to show that A complement union B complement is a subset of A intersect B complement. Okay, so once again, we're going to start off with an element that's in here and show that it's also in here. So let X be an element of A complement union B complement. Well, what does that mean? Well, we can kind of go backwards here. We can say that means that X is an element of A complement, or X is an element of B complement. All we've done is we've deconstructed the union symbol and the definition of union. The union means it's in one or the other. Next, we want to end up with, remember, we want to end up with X as an element of the complement of the intersection. So a lot of times we're going to deconstruct that further and say X is not an A, X is not an A, or X is not in B. Okay, well, if X is not in A or it's not in B, that means it's definitely not in the intersection of A and B, right? It's not in one or it's not in the other. So at least X is not in at least one of these sets. If X is not in at least one of these sets, then it's not in the intersection. X is not in at least one of these two sets. Okay, so if X is not in at least one of these two sets, that means X cannot be in A and B, right? Because if it were, then it would mean that it is in at least one of those sets. And we've almost got it. So for X to not be an element of A and B, that means X is an element of A and B complement. So you see kind of that there's this leap of judgment, or where you really have to logically make some sort of claim to be able to get you from an or statement to an and statement. That occurred up here for us, where we said, well, what does it mean for X to not be an element of A and B? It means that it's not simultaneously in both. What does it mean for X to not be an element of A or X to not be an element of B? It means X is not in at least one of these two sets, which means that X is not in both of them at the same time. So you use these words to build yourself up to where you need to go.